VR Maze was created to understand the effects of virtual reality on user cognition. To study this, we needed an interactable environment that could represent a real-world VR application. In this video, we'll explain how we use the XR Interaction Toolkit, how we procedurally generate perfect mazes at runtime, and how we glue it all together to make a VR game. Our player game object uses a slightly modified XR Origin prefab provided by the XR Interaction Toolkit starter assets sample. To use the Interaction Toolkit, you'll need at least one XR Interaction Manager in the scene to manage the interactions between interactors and interactables. The sample XR Origin game object has a couple of interactors attached to each controller. We use the Poke interactor to allow the player to poke interactables. We use the Direct interactor to allow players to grab and manipulate interactables. The Ray interactor allows players to interact with interactables from a distance. To move around in VR, you'll also need a locomotion system. The XR Interaction Toolkit provides a number of locomotion providers which allow the player to move around the scene in different ways. We use the Snap Turn provider, which allows the player to turn by a set amount each time the turn action is called, and a Continuous Move provider, which moves the player smoothly. Finally, we need an XR UI input module to interact with UI canvases in the scene. We also use a canvas optimizer to increase the performance of our canvases. It prevents UI elements from being processed if they're too far or out of the player's view. The UI setup itself is pretty similar to 3D and 2D projects, however the canvases must all be rendered in world space so the player can interact with them.
The algorithm for generating mazes at runtime uses a depth-first search method using a grid of class objects known as maze nodes. Each node is aware of it having been previously visited by the depth-first search algorithm, its position in the grid of nodes stored as x and y coordinates, and which sides that it should have walls on to form the maze. In order to generate the maze at runtime, a maze generator VR object is created. This uses a given seed and a Boolean value generate a specific maze shape using the generate maze function, which uses the given seed and the Boolean value to decide whether to spawn all checkpoints at once or spawn them incrementally as the player collects each checkpoint. Within its function to generate the maze generator VR object creates a new maze search object, which creates the grid of nodes and immediately runs the depth-first search algorithm to generate the branching paths of the maze. The object is created using a constructor, which with parameters for the size of the maze along the x-axis, y-axis, and the current seeded random. With this data, the object creates a 2D array of the appropriate size and fills it with objects of the maze node class, where each node is given the location of itself within the grid and its isVisited value, which denotes whether it has been visited by the depth-first search algorithm, and that value is set to false. Once the grid is set up, the random is used to generate an XY coordinate, and the search is started from that coordinate immediately after using run search. In run search, the number of previously visited nodes is counted so that it can be terminated if there are no nodes left that have yet to be reached by the algorithm. Assuming that there is at least one node left to visit, the function looks at the nodes immediately adjacent to the current node and checks if they have yet to be visited by the algorithm, making a list of the nodes that are unvisited. If the list is empty, it serves as another termination condition. Assuming that the list has at least one element, a random direction to travel is selected and the remove wall function is called for that direction. So as we can see in this file, this is where we find all of the total unvisited nodes in the grid. This is where we find adjacent unvisited nodes, and this is the loop that we have entered, which contains a recursive call. And after we call remove wall in this loop, the remove wall function takes the current node, the direction to be traveled, and a reference to the list of unvisited nodes. From this information, it sets the Boolean values representing the presence of walls between the two nodes, the node originating from and the node to be moved to be false. After the remove wall function is returned, the run search function is called recursively on the node that was previously selected at random from the list of unvisited adjacent nodes. Once the recursive call has been returned, the node that was selected at random is removed from the list of unvisited nodes. The process of selecting a node at random from the list of unvisited adjacent nodes continues until all adjacent nodes have been visited by the depth-first search algorithm. Once all adjacent nodes have been visited, the algorithm increments the complexity of the maze if the last node was new and not a node that the algorithm was backtracking from. This process results in the algorithm traversing its way through all nodes of the grid, creating branching paths as it does so. By only having gaps in the walls between nodes where the algorithm chooses to traverse, we create a maze with randomly branching paths which fits the definition of a perfect maze. That is, a maze without any loops that is equivalent to a tree in graph theory. Now that our grid of nodes is created, our maze generator VR object can use the maze search object it already has to instantiate the prefabs in the world space accordingly. For every node in the grid, as we can see here, construct maze block is called. This function takes the node's coordinates and the maze search object as arguments. Using the coordinates, it finds the true coordinates in the world space according to the size of our path prefab. This allows us to use different size paths. Otherwise, we'd be limited to a 1x1 path according to Unity's distance calculations. We can then set the position of the paths transform in the world space to the appropriate x, y, z coordinates. Careful to remember that the grid is working in a 2D plane while the world space is 3D. This means that we use our node's x coordinate for the x position, the y coordinate for the z position, and we also use a slight buffer of 0.001 in the y position of the transform's position. While this buffer is not necessary, we found that it worked well with our implementation. We can then instantiate the ceiling at the same x and z positions as the path prefab. For its y position, we need to set it to the wall.transform.localscale.y so that it lines up with the height of our wall prefab. We then proceed to flip our ceiling upside down, but this is only necessary because the prefab that we're using is visible from only one side, and it is designed so that it is viewable from only above in the editor. This allows us to simultaneously be able to see inside the maze from above from the editor's camera during runtime while a player is inside the maze and can see the ceiling from above. Now that the ceiling and path prefabs are positioned appropriately, we can place the walls of our maze. For each of the 4 sides of our node, we check that it should have a wall placed on that side. If it should have a wall, then we place it at the position true x, 1.5, true y. We adjust the x and z position plus or minus 1.38 if it is on the right or left or top bottom respectively. The y position is set to 1.5 to account for the height of the wall. Now that the maze is constructed, the maze generator VR object must place the checkpoints. To do this, the place checkpoints function is called, which take the maze search object used before as an argument. First, the function checks that the player object does not already exist in the world space. This facilitates the generation of multiple mazes during runtime. If only one maze is ever generated, this check is unnecessary. This prevents on generations 2, 3, etc. from the maze generator VR script from creating multiple player objects and then accidentally creating multiple camera objects, which creates a big problem within Unity. At this point, the spawn checkpoints function is called and actually starts the process of placing checkpoints in the maze. Placing checkpoints correctly is surprisingly involved as we are using procedural generation for our mazes, since we do not know ahead of time what the mazes will look like or where the checkpoints will be. We need to cover all possible scenarios. While placing checkpoints, we need to make sure that each checkpoint is placed at a distinct node from each other checkpoint and the player. To begin, the function instantiates the defined number of checkpoints. We are using 5 in our project and places them randomly according to the place randomly function, which you can see down here. All it's doing is taking grid coordinates and translating them to world space coordinates before placing them into the world space. using a pseudo-random value, pseudo-random because it is a randomly selected number, but it will be in the same order of randomly selected numbers every single time if we use the same seed. Once they are placed randomly, the checkpoints are cross-referenced with each other and the player object to ensure that their X and Z positions are not equal. If any checkpoint is at the same position in the maze as another checkpoint or the player, it is again placed randomly and continued to be checked. Once all checkpoints are verified to be at unique locations, they are added to a list and sorted to be in numerical order: checkpoint, checkpoint 1, checkpoint 2, etc., which that is then returned as an array in place checkpoint. This value is used for setting ordered checkpoints active one at a time. At this point, the maze is fully set up and is ready for a player or user to explore and complete checkpoints.
To complete the maze, a player needs to collect several checkpoints. These checkpoints are interactable. The player has to move a ball that's next to the checkpoint into the checkpoint to collect it. The ball itself uses an XR grab interactable component so that the player can pick it up and move it. It also has a rigid body and collider so that it can collide with other game objects. The cylinder has a collider that's a trigger. The onTriggerEnter function will let the maze know that the checkpoint was collected and destroys the checkpoint, if the object triggering it is tagged as ThoroughBall, which the ball is. The game manager is responsible for everything the player does outside the scope of the maze. When the player hits the main menu start button, Setup Level instantiates a random maze, moves the player into the maze, and activates the player's HUD. If the player pauses the game, it locks their movement by deactivating the character controller and activates the pause menu. This method also sets a static property for other objects to read from if their behavior depends upon the game's pause state. Similar to the pause menu, the game manager also provides a method to display the end menu when the level is completed. Return to main menu is called by the pause and end menus. It's basically the inverse of setup level, but it also changes the maze configuration so that the player isn't stuck repeating the same maze every time. To restart the level, we could just call setup level again, as it does not change the maze configuration. The UI is fairly straightforward. Each button's on-click event is set up to call a function in the game manager which changes the state of the game. The start menu allows the player to begin a maze or quit. The pause menu allows the player to return to the start menu or resume the game, and the end menu allows restarting the maze or exiting to the start menu. When the player is completing a maze, there's also a HUD displaying the time and number of checkpoints that have been collected. The HUD, pause menu, and end menu move with the player because they are children of the XR origin. So for an example of the gameplay, the standard usage of the maze will look like this. The game begins with the player in the start room looking at the main menu. If they select the start button with any interactor, a maze is generated, instantiated, and then the players move to the maze. The timer begins running and the HUD's made visible to them. To collect a checkpoint, the player has to grab the ball next to it and move it into it. When the player collects all the checkpoints, the end menu is displayed, and the user can choose to restart the maze or return to the main menu. We hope this example improved your understanding of the tutorial. Good luck with your Unity VR development.